Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome again to my class. Last class we talked about superposition of waves. Now since with the start of the superposition of wave we also get exposed to the interference, but before starting interference I feel that we must have the knowledge of polarization. Therefore, today I will introduce polarization. And in polarization we will talk about linear polarization and circular polarization. We will cover elliptical polarization in the next class. Okay. Now, suppose we have a wave, we always associate the polarization with transverse wave, but in transverse wave we know that there is a electric component and a magnetic component. Okay, transverse wave is made up of electric field and magnetic field, and both these fields must be time dependent and they propagate in certain direction. Okay. A wave is said to be transverse if its electric field and magnetic field they both are oriented perpendicular to the direction of propagation, as well as these two fields must also be perpendicular to each other. Alternatively, what we can say is that E, B and K, the wave vector, they all three must be perpendicular to each other. Okay. And polarization is always associated with the direction of vibration of E, because we know the electric field is a time dependent field in electromagnetic wave, therefore, it will keep varying. Its magnitude is a function of time, it will slowly reduce down and then it will change its orientation and then it will increase in a reverse direction and then again will go down, and this is how it will oscillate. The electric field vector will oscillate slowly. Okay. Similarly, the B field will also oscillate in a plane which will be perpendicular to the E field. B field will oscillate in this plane, the perpendicular one. Okay. And E field is much stronger than the B field, and the magnitude of E is related to B through speed of light in vacuum. It means electric field E, the magnitude of E is C times stronger than B, and what is the value of C? C is 3 into 10 to power 8 meter per second, a very big number, and there is therefore a huge difference between the magnitude of electric field and the magnitude of magnetic field. Therefore, when we shine light on some object, then it is electric field which interacts with the object dominantly, and the interaction of magnetic field would be much weaker. Now, since the dominant component is electric field, we associate polarization with the E field. Okay. Therefore, whenever we say polarization, it means a quantity which is directed along E, the electric field. Okay. Now, you see that in this figure the electric field oscillations, let us pick different color. The electric field oscillation traces a curve and which is in a plane, yeah, and this plane is plane of the paper, while the magnetic field oscillation traces a curve which is again in a plane, but this plane is perpendicular to the plane of the paper. Now, the plane created by electric field oscillation is in the plane of the paper, and if we say that polarization is along E, then with propagation this polarization is creating a plane, okay, and therefore this particular type of polarization is called plane polarization, or the wave is said to be linearly polarized wave or plane polarized wave. Okay. Now, if a linearly polarized transverse wave propagating on a string is incident on a long narrow slit as is shown here, this is a opening of certain width, and a wave who is polarized linearly and its oscillation, the direction of polarization is along the length of the opening, along the length of the slit, then whole of this oscillation will pass through. Okay. And if there is some rotation of the oscillation or of this narrow slit, then it will stop the component of the wave. Okay. It means, or we can say that the slit will allow only the component of the displacement which is along the length of the slit to pass through, and if the slit is allowing this particular oscillation, then we can say that at that instant the electric field is oscillating along the length of the slit, and such a slit will convert a unpolarized light to a polarized light, or more accurately to a linearly polarized light or to a plane polarized light. Now, what is the difference between unpolarized light and linearly polarized light then? Now, we know that a electromagnetic wave is a transverse wave and it has a certain direction of propagation, and perpendicular to the direction of propagation we have electric and magnetic field orientation. Now, since E and electric field and magnetic field are functions of time, they will keep changing their amplitudes, but they may take any orientation while propagating along the medium. Yeah, they may at one instant of time they would be oriented like this, while on the other instant they may take this orientation, in the next instant they may take this orientation. The orientation of electric and magnetic field is completely random, and if this is the case, the wave is said to be unpolarized, while a wave which is propagates like this are waves in which the electric field vector, oscillation of electric field vector traces a plane with propagation. Such a wave is called linearly polarized light or linearly polarized wave or plane polarized wave. Now, let us go deeper into this concept. The first thing which we should understand is that light is an electromagnetic wave and it consists of rapidly varying electric and magnetic field. Since electric and magnetic fields are time dependent, therefore, they vary very rapidly. The electric field and magnetic field are perpendicular to each other, this we have understood, and they both are also perpendicular to the direction of propagation of wave. Okay. And polarization is an important characteristic of light which is related to the electric field vibration. Okay. It is always along the E field orientation. Okay. But this statement is strictly true for isotropic media. As discussed earlier, isotropic materials are materials in which the properties of the medium are not direction dependent. The isotropic medium will have same property in this direction as well as in this direction as well as in this direction. In all the directions, the isotropic material will exhibit the same properties, while in anisotropic material the properties, the optical properties of the material become direction dependent, okay, and these materials are called anisotropic. Now, for isotropic material, this definition holds very good. We will talk about anisotropic material in our later classes, but for now on, it is correct to associate polarization with the direction of E field. Why? Because E field is dominant as compared to the other field, which is our magnetic field. Now, before moving ahead, we must understand what is plane of vibration. Okay? The plane of vibration is defined as a fixed plane which consists both electric field vector E and propagation vector K. Okay? And from this figure, what you can see is that the red curve shows the evolution of tip of electric vector, while the blue curve traces the tip of B field, the magnetic field. Okay. Now, this vertical direction is the direction of E and this is the direction of propagation. The direction of propagation is represented by propagation vector K, okay, and K is this and a unit vector, say A. Unit vector is a vector quantity which indicates the direction, and mod of K is K, which we already defined, which is equal to 2 pi by lambda, okay, and the vector nature is coming from this A cap, which is unit vector, which is in the direction of propagation. Okay. Now, using E and K, we can trace a plane, and this plane is called plane of vibration. Now, once the plane of vibration is understood, let us move further in understanding the concept of polarization, or in particular linear polarization, mathematically. Okay. Now, consider two orthogonal optical disturbances. Now, first is Ex and second is Ey. Okay. X and Y represents the direction of vibration. It means that Ex represents a field which is oscillating along x axis, and Ey represents a field which is oscillating along y axis, and Ex is equal to I cap E naught x cos kz minus omega t. Kz minus omega t is phase, E naught x is amplitude, and I cap is nothing but unit vector along x axis. Similarly, the expression for Ey is equal to j cap E naught y cos kz minus omega t plus epsilon. Here again j cap is nothing but unit vector along y axis, E naught y is the amplitude, and kz minus omega t plus epsilon is phase. Okay. But here epsilon is the relative phase difference between the two waves, okay, and the usual phase is in the form of kz minus omega t. Now, the addition of a positive phase, which is epsilon, means that the cosine function in equation number 25 will not attain the same value as the cosine in equation number 24. Let us understand it in a different way. We can write equation number 25 as j cap E naught y cosine of kz. Let us take omega out of the bracket, and then we will have t minus epsilon by omega. Okay, this is the modified expression. Now, if you compare equation number 24 with this modified expression, then what you see is that in equation 24 the phase part is kz minus omega t, while in this modified equation 25 the phase part is kz minus omega in bracket t minus epsilon by omega. Okay. This epsilon by omega factor is being subtracted from time. It means in equation number 25 the overall phase is running slower, it is a behind. Okay. And this is what exactly is being said in the line here. The addition of a positive epsilon means that the cosine function in equation number 25 here will not attain the same value as the cosine in equation 24 until a later time epsilon by omega. Okay. Equation number 24 has this phase, it evolves in time, and the same phase would be achieved by equation number 25 only after an additional time, and this additional time is epsilon by omega, which clearly says that equation number 25 is lagging behind equation number 24, or in other words Ey is lagging behind Ex provided epsilon is larger than 0. Okay. Ey lags Ex by epsilon. Okay. Now, if epsilon is negative quantity, then Ex will lag Ey. Yeah. Now, let us calculate the resultant. How to calculate the resultant? We will again resort to superposition principle. We will add these two waves. Now, as in the previous slide we assumed that these waves are orthogonal, and these are the fields which are vector quantity, and therefore, we will have to take into account this vector nature, and this addition would be vector addition. Okay. Now, here in equation number 26 we are adding Ex and Ey vectorally, okay, because these are two perpendicular components. Yeah, Ex is perpendicular to Ey. Okay. Now, if epsilon is 0 or integral multiple of 2 pi, the waves are said to be in phase. We know it, yeah, we understood it in our last lecture. Okay. Now, in the case when epsilon is either 0, epsilon is our initial phase, yeah. If epsilon is either 0 or multiple of plus minus 2 pi, integral multiple of plus minus 2 pi, then the resultant will have this expression which is given by equation number 27, and the resultant E is equal to I cap E naught x plus j cap E naught y, and the phase part is cosine kz minus omega t. Okay. Now, what is the state of polarization of this resultant wave? How to know about this? Now, you see that it is a vector addition. We are adding Ex and Ey, then let us plot it. Yeah. If you plot it, if let us put Ex on x axis and Ey on y axis. Okay. Now, the magnitude here is E naught x along x axis and E naught y along y axis. Okay, there would be some magnitude here in x direction and some magnitude here in the y direction, and the resultant would definitely be pointing here, and it would be in the resultant will oscillate in first and third quadrant. Yeah, this would be the oscillation direction of the resultant. That would again be a linearly polarized wave, isn't, because the resultant oscillation is again linear, it is confined to a certain plane, and with propagation this linear oscillation will generate a plane. Therefore, this wave is plane polarized or linearly polarized. Okay. The waves advance towards a plane of observation where fields are to be measured. Yeah. There one sees a single resultant E oscillating along a tilt line. Okay. You see that the resultant is oscillating here, but it is tilted by an angle theta. How to know theta? Very easy. Yeah. This is how we can calculate theta. How it is done? It is a, we have two part, E naught x cos kz minus omega t and E naught y cos kz minus omega t. Y by x will give us the angle. Yeah. If you want to calculate theta, how to calculate? Take y component and divide it with x component. The y by x value will give you tan theta. This is what is done here. Okay, E naught cos kz minus omega t is kept in numerator and E naught x cos kz minus omega t is kept in the denominator, and cos will go away, and then tan theta would be equal to E naught y upon E naught x, which are nothing but amplitudes of Ey and Ex respectively. From here we can get the orientation of the resultant Ey. Okay. Now, this angle, as you can see from equation number 28, it depends upon the amplitudes. Now, depending upon the relative amplitude of the two wave, the resultant will change its tilt. Okay. The theta value will vary, and this variation would be directly proportional to the relative amplitude of the two waves. Now, let us consider another case. Till now we were considering that epsilon is either 0 or integral multiple of 2 pi. What if epsilon is an odd integral multiple of plus minus pi? Under this case, the two waves will be out of phase by 180 degree, by pi radian, and the resultant now will be expressed differently, and this is expressed here by equation number 29, and the difference between the previous resultant disturbance, which is given by equation number 27, and this new resultant is that there is minus sign instead of plus sign. Okay. Here in equation number 27 you see that there is a plus sign, while in equation number 29 you see there is a minus sign. How would it introduce a difference? Now, let us again plot Ex and Ey, Ex here and y component here. What will happen here? The plane of vibration, now the resultant here you see it will now be in this, along this line. This would be your resultant. Why? Because x, the y is minus here, y component is in opposite direction, x is pointing here at particular instant, y is here. Okay. The resultant therefore would again be although linearly polarized, but plane of vibration has now been rotated from that of the previous condition. Okay. Resultant is again a linearly polarized light, but there is a rotation of plane of vibration. Okay. Now, you see that whenever we represent a plane polarized wave, the resultant always looks like a double headed arrow. What does this represent? A linearly polarized wave or a plane polarized wave? Okay. Now, if this is the representation of a linearly polarized wave, what will be the representation of a unpolarized wave? Now, since in an unpolarized wave the electric field vibration can take any orientation, therefore, usually the convention to represent an unpolarized light is this. Okay. This is used for unpolarized light. Okay. Single double headed arrow stands for a linearly polarized light, and multiple double headed arrow which forms star like structure, it is used for unpolarized light. Now, after this analysis, what we can see is the following. In an unpolarized light, if you know the orientation of electric field at a particular instant of time, suppose t is equal to t naught, then you cannot predict or you cannot forecast the orientation of electric field at a later time. While in a linearly polarized light, if you know the orientation of electric field at some time t is equal to t naught, then at a later time you can predict its orientation. You know that it will always be in the same orientation. Okay. It means that we can say that once a wave is polarized, the predictability comes in our hand. If you can predict the orientation of the electric field, once you know the orientation, once you know the earlier orientation, then the wave would be polarized. Okay, I repeat it again. In an unpolarized wave, if you know the orientation of field at some earlier time, then you cannot predict its orientation in later time. While in a polarized wave, if you know the orientation of electric field at some earlier point in time, then you can predict its orientation in some later point in time. This power of predictability comes in our hand once the wave is polarized. Okay. Having understood this, let us discuss the second type of polarization. Okay. What is the second type of polarization? Circular polarization. Okay. Till now we were considering two waves which were orthogonal, that is they were oriented into directions which are 90° to each other, and they were having different amplitudes. Okay. Now, here we will consider waves which have equal amplitudes. E naught x would be equal to E naught y now, and we will assume that E naught x is equal to E naught y and it is equal to E naught. Okay. And in addition to this, their relative phase difference, which is epsilon, is equal to minus pi by 2 plus integral multiple of 2 pi. Okay. Now, let us consider the simplest case where m is equal to 0, then in that case the relative phase difference between the two orthogonal waves, the two overlapping orthogonal waves, is minus pi by 2. Okay. The simplest case is epsilon is equal to minus pi by 2. With this, let us rewrite the expression for wave. Okay. Two assumptions here are equal amplitudes and relative phase difference is minus pi by 2. With this, Ex can be expressed as I into E naught, okay, E naught is here, and cos kz minus omega t, and Ey is equal to j cap E naught again, and then sin kz minus omega t, no epsilon right now. Okay. Where is epsilon? It is eaten up by this function. You see, in the first expression there is cosine term, while in the later second expression it is a sine term. Pi by 2 is now absorbed here in sine function. Okay. And the amplitudes are the same, okay, as per our assumption. Okay. Now, let us calculate the expression for the resultant disturbance. How to calculate? Add them vectorially. Okay. If we add them, we will get this expression, the resultant one. Okay. Now, it has E naught came out of the bracket y, it is a common. Now, the scalar amplitude of E, how to calculate the amplitude of E? amplitude of E is calculated using this formula. Yeah, E is a vector quantity, take dot product with itself and then square root it, this will give you the scalar amplitude of vector E. Okay. It is a constant. Yeah, this resultant vector E has an amplitude which is a constant, okay, but the direction is time varying. The direction of E is now time varying. Okay. Now, contrary to the linear polarization case, the direction of the field is not restricted to a single plane here. Okay. I repeat for clearer understanding. The resultant field E, you see, has a constant amplitude. Okay. The amplitude is not varying with propagation or with time, but the direction of E field is now varying. Okay. Till now we were in the habit of seeing this kind of wave, okay, whose amplitude is function of time. You see the magnitude of these arrows are reducing here and then they are changing directions, and this is how we trace a sinusoidal wave, is not it? Yeah. The amplitude was function of time. Whenever we say a field is function of time, then it is amplitude which was varying with time or varying with z, propagation, space. But here in case of circularly polarized light, what we saw is that the amplitude is constant, it is not varying. Then where does the time dependence comes in? The time dependence comes in from the time dependent direction. Okay. In linearly polarized light, the electric field was vibrating in a particular plane, its direction of vibration was not changing with the propagation, it was neither function of time nor function of space. But in case of circularly polarized light, the direction of E field is now changing with propagation, it is a function of time and space. However, its magnitude neither depends on space nor on time, it is a constant quantity. Okay. Now, with this in mind, let us now assume some arbitrary point in space in direction of propagation, and that point is z is equal to z naught. Okay. We are assuming that wave is propagating in z direction, and at a particular point z is equal to z naught, and at this point when the wave reaches at point z is equal to z naught, assume that the time counting starts from there, that is time is equal to 0 there at z is equal to z naught. Under these two conditions, we can rewrite equation number 30 and 31, okay, and the new expression for Ex, vector Ex and vector Ey are given by equation number 33 and 34. Okay. These are the two waves which will overlap. Okay. Now, if you square 33 and 34 and add them up, then you see that they traces a circle. It means the resultant would be a circularly polarized light, okay, because when you trace a circle out of the tip of the electric field vector, then the radius of the circle, irrespective of where you are on the circumference, the radius is constant, it does not vary, okay, and this is what is being said here also, the scalar amplitude is constant. Okay. Now, what is varying? The electric field vector will keep changing its direction, at some point of time it would be here, next here, next here, it would keep changing its direction. Okay. But this change in direction would not be random. Why? If this would be random, then we would lose the power of predictability, and we have already discussed that if orientation of E field is predictable, then only we can say that the wave is polarized. Okay, that much information must be in our hand. Okay, then let us see further what happens with equation number 30 and 33 and 34. Okay, equation number 33 and 34 is written at z is equal to z0 and time t is equal to t0. Yeah. Now, this particular point is given by this reference. Okay, say this is the reference. On this horizontal axis we expressed vector E, on this vertical axis it is vector Ey. Okay. On horizontal axis it is vector Ex, on vertical axis it is vector Ey, and at certain point in space which is z is equal to z0 and time t is equal to 0. Suppose this is the direction of the resultant field, which we call reference axis. Okay. Now, since this is the reference axis, we will start the calculation from this reference axis. Okay. Since we are assuming time is equal to 0 here at this reference axis, as soon as we start from here, time will increase in positive direction here. Now, time slowly will increase. Now, suppose at a later time which is given by k z naught by omega, where did we get this expression from? We know that E is equal to E naught. Suppose a vector quantity is here and then cos of omega t minus k z naught. Okay. Now, how did we choose later time? From this expression. When will this expression will become 0? This expression will become 0 at a time point which is given by k z naught by omega. Okay. This we choose as our later time. This is given here. Yeah. At this point, what will happen? The field at this point, what will happen? The Ex component. What is the expression of Ex component? It is given by equation number 13. If you replace t by k z naught by omega here, then you will get 0 here. Now, let me write it here for more clarity. Ex is equal to I cap E naught cos k z naught minus omega t. This is equal to I cap E naught cos k z naught minus omega. Now, t has this value k z naught by omega. The omega will go away and k z naught will go away with k z naught. Therefore, we would be left with this value, and this is what is written here. Similarly, we can calculate Ey. If the phase is 0, then sine which is sitting here, the sine of 0 would be equal to 0, and therefore therefore Ey would be equal to 0. Okay. And therefore, at a later initially the wave was initially along the reference axis direction, and at a later time the x component has some finite positive value and the y component has 0 value. Okay. X component has some finite value and y component has 0 value. It means from the reference axis direction wave came here in this, the electric field resultant electric field rotated in this direction as shown by this arrow here. Okay. Initially it was in along reference axis direction, now the resultant is along Ex vector direction. Okay. And therefore, the resultant is along the x axis. Okay. Therefore, we can say that the resultant electric field vector E is rotating clockwise direction at an angular frequency omega as seen by an observer towards whom the wave is moving, a very important concept. Initially the wave was along this reference axis direction, now the wave is on x axis and E is the resultant E is pointing along x axis. Yeah, the whole rotation is clockwise fashion. This is how the wave is rotating. Yeah, the rotation is like this, which is clockwise rotation, and we are standing in the front and we are looking into the source. Okay, the light is coming towards us, and as an observer we are looking into the source. Under this case, if we see the resultant electric field vector tip rotates along clockwise direction, then such a wave is called right circularly polarized wave. I repeat, if we are looking into the source and seeing the resultant electric field is rotating clockwise direction, or more accurately the tip of resultant electric field vector is tracing a circle in a clockwise direction, then this kind of polarization or this kind of wave is called right circularly polarized wave. Okay. And this is also very much clear in this figure. The tip of the electric field vector is rotating in a clockwise fashion. In the case when we are looking into the source, the light is coming towards us, and this wave is called right circularly polarized. Okay, this is a very important concept. We must look into the source, yeah, and light must be coming towards us. Therefore, the referencing is very important. We must look into the source, light must be coming towards us, and under this condition, if the tip is rotating in a clockwise fashion, then the wave is called right circularly, then the wave is right circularly polarized wave. Okay. The acronyms for right circularly polarized wave is RCP, right circularly polarized. Similarly, if the relative phase difference is pi by 2 and then integral multiple of pi, then what will happen is that there would be a minus sign here instead of plus sign. The resultant will have minus sign. Okay. And if this is the case, then the resultant will trace, the tip of the resultant field will trace a circle in a anti-clockwise fashion, and such a wave is called left circularly polarized or LCP. Okay. Earlier it was RCP, now it is LCP. Now, this is equation number 35 represent an LCP, while equation number 32 which is given here, this represent an RCP. Now, let us add these two equations. Yeah, the only difference here is in sign. Okay. Now, if we add them up, this is the resultant. If you add LCP and RCP, then you get equation number 36, which clearly is pointing along x axis and which is a linearly polarized light. Okay. Which means out of left circularly and right circularly polarized light, we can again generate a linearly polarized light. A more generalized statement is, using two orthogonally polarized light, we can generate any type of polarization, or alternatively any type of polarization can be expressed in the form of orthogonally polarized light. Okay. X polarized and Y polarized light are orthogonal, left circularly polarized and right circularly polarized light are orthogonal. So, using these two pairs, we can generate any kind of polarization. Now, you can see here the formation of circle in a circularly polarized light. You see at some instant where suppose t is equal to 0, you see that Ex is equal to 0 and Ey has some finite value equal to E naught. Therefore, the resultant would be here. At some later time, suppose t is equal to delta t, Ex has gained some value and E naught is reducing. Therefore, the resultant is not now pointing towards y axis, it has this orientation now, it has rotated clockwise fashion. Now, again if you move further delta t plus delta t, E resultant E came here, E now Ey is reducing down and the resultant in slow is in the next interval of time delta t plus delta t plus delta t suppose. Now E is now is along x axis and slowly you are seeing that it is tracing a circle with propagation, okay. And this particular light is doing clockwise rotation and therefore it is called right circularly polarized light, okay. But if you see it in space, then this circularly polarized light will form a helix, yeah. Initially it would be in at some time and then slowly it will create this type of helical structure. The tip of electric field vector will trace a helix in space, okay. And if you see now there would be an axis of symmetry of this helical structure, and if you point your eyes along this axis of symmetry, then you will see a circle, okay. But if you take a video of this tip, then the tip will trace a helical structure, okay. Right circularly polarized will form one type of helical structure, left circularly polarized have the opposite sense of rotation, therefore this helical structure would be formed differently. This is all for today. I end my lecture with this, and thank you all for your presence and listening me.